So in the last video, we talked about atomic radius, and here we want to move on to a couple more trends. First, ionization energy. You need to memorize what the definition of ionization energy is, but let's try to help you get there. So remember we talked about an ion is an atom that gains or loses an electron. We said if you lose an electron, you're going to become positive, a cation. If you gain an electron, you become an anion, a negative ion. So ionization energy is the amount of energy it takes to remove the attraction or overcome that attraction of nuclear charge and remove an electron from the gaseous atom in the ground state. For pre-IB, we kind of want to know that definition. That's the amount of energy you need to remove an electron in the gaseous state. But for Regents, if you just understand that's the amount of energy it takes to remove an electron, I'm happy with that. It gets Sometimes they'll ask that question as a part 2 on the Regents, so you have to be able to write that out. The amount of energy required to remove an electron. When an atom loses one electron, it's going to form a positive one charge. And we know that the amount of energy it takes to remove this first electron is called the first ionization energy. If I was to ask about removing the second electron, we would call that the second ionization energy, and so on and so forth. So let's talk about what's happening. As you go across the period, so as you go left to right across the period, it becomes more difficult to remove an electron. So let's think about, we talked about in the last video that as you're going left to right, you're adding more protons, the nuclear charges increase, and those electrons are being pulled in so tightly as we're moving across the periodic table. Since they're pulled in tight, it's going to be difficult to remove an electron. Since it takes more energy to pull it away, the ionization energy goes up. So ionization energy is how much energy it takes to remove an electron. Since there's greater attraction on there as we're moving to the right of the periodic table, that amount of energy increases. As you go down a group, we said that there are more shells and there's more shielding. So the electrons on the outer rings don't feel the attraction as much to the nucleus. So it's easier to pull an electron away from those bottom levels where there's so many rings. So since it's easier at the bottom, that means at the bottom it doesn't require as much ionization energy. The amount of ionization energy needed goes down. So in summary, what you need to know about ionization energy is what it is, the amount of energy needed to remove an electron, that as you go across the period, it goes up because there's a greater nuclear charge. The shielding remains the same, but the nuclear charge is increasing. For pre-IB, we're going to talk about that there are exceptions to this for half and full orbitals. For groups, ionization energy decreases as we go top to bottom because there's more shielding, because there's more energy levels. Therefore, the electrons don't feel the attraction as much as you go down, so it's easier to pull it away. The second ionization energy would be the amount of energy needed to remove the second electron. That's always going to be greater than the first. It's going to become more difficult to remove another electron. The third is going to require even more energy than the second. The same idea, the amount of energy, the third electron going in. For SAT2, this idea of electron affinity also comes up. It's kind of the opposite of ionization energy, meaning the amount of energy released when an electron is gained. But it follows the same trend as ionization energy, that it increases as we go up and to the right of the periodic table. We just want to explain a little bit about what we were just mentioning, that for ionization energy for half and full orbitals, the values are going to change. It's not a straight pattern for ionization energy across the period, so I just want to show you what's happening. As we go from hydrogen to helium across period 1, helium has a greater ionization energy, which makes sense. We're in the same period. The shielding is the same, meaning we have the same number of shells. Nuclear charge increase for helium, so it's harder to remove the electron for helium. Then we get to lithium. Lithium is now in the next period of the periodic table. So lithium has a lower ionization energy, meaning it's easier to remove an electron from lithium because it has the 2 electrons on the first shell and the second shell holds 1. So this electron is further out from the nucleus. There's more shielding, and that shielding outweighs the greater nuclear charge. So the ionization energy, meaning the energy needed to remove that electron, actually goes down. Be is higher than Li because it has the same shielding. These are both in period 2. But Be has a greater nuclear charge, which means the electrons are held more tightly, so it's harder to remove. Then we go to B. B has a lower ionization energy. It has the same shielding, meaning that all 3 of these elements, lithium, beryllium, and boron, are all in the same period. But the nuclear charge has increased. But when we remove an electron from B, we end up giving it a full s orbital. So B gladly gives away its outermost electron, because if we look at the electron configuration here, as an atom, boron is 1s2, 2s2, 2p1. As a boron ion, it's 1s2, 2s2. So we're making the s orbital full, which is more stable to have a full orbital or a half full orbital. So here's actually a picture of what ionization energy looks like as we go across the table. And these dips have to do with if we have a half full orbital, it's actually more stable, or a completely full orbital, it's more stable. So if we could remove an electron to make an atom have a half or full stable orbital, it will do so, and it will require less energy then to remove that electron. In general, this is the trend that we observe for ionization energy. As we go up and to the right, it gets stronger, or if you go down to the left, it decreases. So ionization energy, meaning the amount of energy we need to remove an electron, is strongest all the way to the right, the nonmetals. If we think about what's happening as we're going left to right, we're increasing nuclear charge, making it harder to remove an electron. It gets easier as we go down because we have more shielding and more energy levels, so it's easier to pull away. The next trend we want to talk about is called, has to do with the ionic size, which means that as a metal or nonmetal, what happens to your size? Metals lose electrons, so what's going to happen is they're going to get smaller. So here's an Na atom. Electron configuration is 281. There are 3 shells. Here's an Na ion. The ion is +1, which really means -1, so it loses a whole shell, so then it's just 2,8. So the ion has 1 whole less shell than the atom, so it's smaller. So here's a picture of an Na atom versus an Na ion. Magnesium atom versus ion. You see that the ions are smaller because they lost a whole shell to become an ion. Nonmetals are not the same in that they gain a shell, but the electrons are going to repel each other when they're added. So for example, a fluorine atom is 2,7, the ion is 2,8. It has more electrons. So you're adding more electrons are going to repel each other because electron and electron are negative charge, and that repelling pushes the electrons away from each other and increases the size of the ion. So not that it gains a shell, but the addition of the electron causes the repulsion to increase and the size to increase as well. Here's a picture showing you the atomic, which is atom, versus ionic, radius. Atomic, or like here it's showing you the size. Lithium, sodium, potassium, rubidium, we know it gets bigger, it's showing you the size. But I just want you to compare the atom to the ion. The atom is bigger than the ion. Atom bigger than the ion. So for all metals, since metals lose electrons to become ions, the atom will always be bigger than the ion. Atom bigger than the ion. Atom bigger than the ion. For nonmetals, it's the opposite. The atom, or atomic radius, is smaller than atomic radius, ionic radius. So here's the atomic radius of nitrogen. Here's the ionic. The ion, when it becomes an ion, it gains electrons. Those electrons repel each other, so it gets bigger. So atom, ion, atom, ion. It's just showing you as you go across. For pre-IB, you want to know that the term isoelectronic means the same number of electrons. So for example, sodium ion has the same number of electrons as a neon atom. So just the same number of electrons as this word isoelectronic, and that comes up periodically. Last trend we have to know is called electronegativity. Electronegativity is a tendency to attract electrons to yourself. We need to know that as you go left to right across the periodic table, it goes up. As you go down a group, it gets smaller. And the most electronegative element is fluorine. It is in the top right, so it's following that same trend for that ionization energy follows up and to the right. And we need to know that group 18, so as we go up and to the right, we talked about ionization goes up. Same idea, but group 18 does not have a high electronegativity because group 18 is already stable. They have a full valence shell. So while ionization energy goes all the way to the right, electronegativity goes up and all the way over to the right, but it stops at fluorine. Fluorine is the most electronegative element of all the elements, meaning that it attracts electrons to itself the most. Remember that these don't group 18 because they already have a full shell of 8 valence electrons. They do not need to attract any more electrons, so they are not going to have high electronegativity. So highest electronegativity goes up and to the right, stops at F. Highest ionization energy goes up all the way to the right, stops at He, because ionization energy was something different with how much energy it takes to remove an electron. Since group 18 is so stable, it's going to take a lot of energy to remove an electron from one of those atoms.